Alright, welcome to Module 12, Part 3. This is Chapter 9. This is the last bit, and we're just going to talk about molecular orbital theory. Okay, so not all bonding can be explained by most things we've learned in Chapters 8 and Chapter 9, like Lewis structure, hybridization, and the Vesper theory. Molecular orbital theory actually uses what we term wave functions to describe electrons in the molecule. Okay, and so these are very similar to atomic orbital theory, except this is talking about molecular orbitals. And so similar to atomic orbitals, each of these molecular orbitals will hold two electrons with opposite spins. Okay. However, the molecular orbitals are associated with entire molecules and not a single atom. That's very important. So for example, we could look at hydrogen gas, which is a combination of two hydrogen atoms, each with one electron in the 1s. Okay. When these two atomic orbitals overlap, we form two molecular orbitals. Okay. One of those is going to have an electron density between the nuclei, okay, and this is called our bonding molecular orbital. This orbital has lower energy than the atomic orbitals, and thus it's more stable. Okay, this is part of the reason why a covalent bond is formed, because it's more stable, takes less energy. And then the other one has little electron density between the nuclei, and this is called anti-bonding molecular orbital. All right, and this orbital has more energy than the atomic orbitals. Okay, a couple symbols here that you should know is this sigma star 1s means that we have a sigma molecular orbital. This is a non-bonding molecular orbital, anti-bonding, which we put the little asterisk, and 1s. We're talking about it's in the 1s, right? Because that was the two atomic orbitals. Without the star, we're talking about the bonding molecular orbital. Okay, and molecular orbital is a lot of times abbreviated with a MO. So the energy level diagram or molecular orbital diagram shows the energies of the orbitals in a molecule. Okay, so each atomic orbital interacting in a covalent bond formation is written on both the left and right. So here's one hydrogen atom we write on the left, the other hydrogen atom we write on the right. Okay, and so that means that basically those two are going to come together and form the molecular orbitals that are then placed in the center. Okay, and what you should note is that the anti-bonding molecular orbital is going to be empty, and the bonding molecular orbital is filled with two electrons with opposite spin, less energy, and that's because one electron from the hydrogen atom on the right, one electron from the hydrogen atom on the left combine in the lower energy first, and so this is filled where the anti-bonding is vacant. Alright, so we can write electron configurations, basically where we write sigma 1s2, which means there's two electrons in the sigma 1s molecular orbital. Okay, so we can write it just like we do for electron configurations. Well, when we're talking about molecular orbital theory, the stability of a covalent bond is directly related to its bond order. Okay, and we can just calculate bond order by taking it equal to 1/2 is equal to the number of bonding electrons minus the number of anti-bonding electrons. Okay, so number of bonding minus the number of anti-bonding. You can get a fractional bond. Okay, that is possible, but usually you'll get like a bond order of 1, which says there's a single bond existing between that, bond order 2 for double, bond order for 3, etc. So we can look at an example of hydrogen versus helium. So hydrogen gas and helium gas. So for the hydrogen, like we said, we have one electron in one hydrogen atom, one electron in the other hydrogen atom. They're both in the 1s. They both donate an electron to these molecular orbitals, which is going to fill the lowest energy first. So we have a sigma 1s. Okay, there are no more left to donate from these hydrogen atoms into the anti-bonding. Okay, so then in order to calculate the bond order, 1/2 from the bonding minus the anti-bonding, 2 minus 0, so we equals 1, which says there's a single bond between these two hydrogens, which is true. Okay, if we did this for helium, He2, here we notice that we have 2 electrons from this helium atom, 2 from this helium atom, based on the periodic table and how many valence shell electrons it has. Those then are donated in, and so we actually fill the bonding and the anti-bonding molecular orbitals. Okay, and if we calculate that bond order, we actually get 0, which says that He2 does not exist. Okay, so it kind of helps you tell if a molecule can actually exist. Here's a list of rules for combining these atomic orbitals into molecular orbitals. These are pretty straightforward if you just think back to atomic orbitals, so I'm not going to go through these. However, you should be familiar with them. Well, we can look at the molecular orbitals for more complex compounds like lithium, okay, Li2. So 1s orbitals combine with 1s orbitals. So here we have our lithium, which if we base it on the periodic table and the valence shell electrons, lithium has 3 valence shell electrons, 2 in the 1s, 1 in the 2s, okay? And so this is one lithium atom. We're combining it with another lithium atom, which is shown here on the right. And so what it's saying is that electrons in the 1s here are combining with electrons in the 1s here to form these molecular orbitals. Then the 2s electrons will come together to form the anti-2s, or I'm sorry, the sigma 2s molecular orbital and the anti-sigma 2s non-bonding atomic or molecular orbital. Okay, so when we look at what happens in bonding, these core electrons, which are everything except, or I'm sorry, the core electrons don't contribute to bonding, and we just typically ignore those. Okay. So here, the 2s orbitals are farther from the nucleus, and thus they interact more effectively. Okay, this is going to result in more energy. And so if we calculate the bond energy here of lithium, basically we find that the bonding electrons, there's 2 in the 1s, 2 in the 2s for a total of 4. And there's only 2 in the anti-bonding, right? This one's empty, so 4 minus 2 is 2, times 1/2 is equal to 1. So a single bond is present for these molecular orbitals as well. Alright, so it gets a little more complicated when we get to 2p atomic orbitals. Okay, so for atoms with both s and p orbitals, there's 2 types of interactions we can have. Either the s and p orbitals that face each other overlap in a sigma fashion. So if these two could face one another, they're going to overlap in that sigma fashion. Okay, so we have our bonding and then the anti-bonding. Or the other 2 sets of the p orbitals, which are these two, okay, are going to overlap in a pi fashion, where you have your anti-bonding and then your bonding, right, the above and below that axes, and then once again here as well. Okay, so just if you remember back to part 2 of chapter 9, you can remember how these p orbitals come together to form these pi bonds. And so the resulting molecular orbital diagram is going to look something like this figure on the right. It's a little more complex. Okay. So notice that the 2s atomic orbitals are going to be lower in energy than the 2p atomic orbitals, right? So the 2s are lower than the 2p. And the sigma 2p binding molecular orbital is lower in energy than the pi bonds of the 2p molecular orbitals. Also note there's 2 degenerate molecular orbitals for both the 2p pi bonds. Okay. So basically these are each a molecular orbital, but they're the same between those other 2 that we just talked about, right? So back here, these 2 are going to be kind of the same when we talk about pi 2p and the pi star 2p, right? So basically, we made a diagram that assumes there's no interaction between the 2s orbital on one atom and the 2p atom on the other, but this does actually happen. Okay. So anytime you're drawing the molecular orbital diagram for something that has both s and p orbitals, you should be able to draw it in this way. And your molecular orbital diagram is going to be in this order, with the sigma 2s, then the anti-bonding 2s, right? Because those are, the anti-bonding is always higher in energy. Sigma 2p is going to be lowest in energy, then the pi 2p, then a pi star 2p, and the sigma star 2p. Okay, so those are kind of opposite. Right, and so let me just backtrack real quick. So basically, when you fill these, you're always filling the lowest energy first, right? So you take electrons from one atom, the other atom, fill it lowest first. Same thing here when we draw our 2p atomic orbitals. So the interaction of one s orbital and one p orbital increases the energy difference between the sigma 2s and the sigma 2p. Okay, so the smaller p block elements in the second period have a sizable interaction between the s and p orbitals, and so this just flips the order of the sigma and the pi molecular orbitals in these elements. So there's certain elements which are basically listed over here. So B2, C2, and N2, which basically the sigma 2s and the sigma 2p, okay, are actually going to be swapped, and now the sigma 2p is above this pi 2p, okay, and the sigma 2s is actually going to be about the same, okay, so this is where you're having that change. The last part of this is just paramagnetic and diamagnetic. So molecules with one or more unpaired electrons that are attracted to the are attracted to a magnetic field are called paramagnetic. If they have no unpaired electrons and are weakly repelled by a magnetic field, it's diamagnetic. So basically all we're looking for, so we can see like with B2 that basically you have unpaired electrons, that makes it paramagnetic. And these are all the molecular orbital diagrams, okay? Here we can see that we have paired electrons, and so it's diamagnetic. For oxygen gas, you can see you have unpaired electrons in this star 2p, which makes it paramagnetic, and so forth, okay? And so really you should just be able to say if it's paramagnetic or diamagnetic. That concludes Chapter 9. Chapter 9 is pretty tough at the end. It's a lot going on. Anyway, make sure you read through the book. That should help in ask me if you have any questions.